So for us to understand the logic behind the previous theorem, let's look at a few illustrations. So for our first item, we want to evaluate the limit of 1 over x cubed minus 4 as x approaches negative infinity. So note that x is in the denominator and that the denominator will proceed to large negative values while the numerator stays constant at 1. So this means that our denominator would be a really large negative value, and so the limit of this function as x approaches negative infinity will be 0. So if the denominator becomes really big, then the value of the limit will now be 0 since x approaches negative infinity. Okay? And next, so now we need to evaluate the limit of 5 minus 2 over x squared as x approaches infinity. So here, let's just write that down. The limit of 5 minus 2 over x squared as x approaches infinity. We can separate this limit into two different limits. So this is now equal to the limit of 5 as x approaches infinity minus the limit of 2 over x squared as x approaches infinity. Okay, so for our first limit, since 5 is a constant value, then this is just 5. And for the second limit here, the limit of 2 over x squared as x approaches infinity, note that, again, the numerator remains constant at 2, while the denominator holds x squared. And since x would approach infinity, our denominator will proceed to large positive values, right? So this means that the value of this limit is simply 0. Thus, we have here 5 minus 0, which gives us a final answer of 5. So in other words, if we have the limit of 1 over x as x approaches infinity, or if basically the denominator is approaching a large value, then that limit would be equal to 0.